So I was talking about single logarithmic equations. That's what we are going to be treating today. I said record that in index notation 16 is written in this form. That is to say that, watch this. Instead of writing 16, you can write 2 times 2 times 2 times 2. This is the same as 2 raised to the power of 4. That is 2 raised to the power of 1, 2, 3, 4. And this expression is known as the index notation, right? And that simply implies that in mathematics, this is the implication sign. That implies that we can say 16 is the same thing as 2 raised to the power of 4. Where 16 is a number 2. 2 is the base and 4 is the index of power. You can say here 16 is the number, 2 is the base, and 4 is the index, otherwise known as power. However, we can also say that 4 is the logarithm of 16 to base 2. You can say that, let's say, however, take down these notes. You can refer to 4 as the logarithm of 16 to base 2. You see that? And that implies that 2 raised to the power of 4 is equal to 16. And we can say the logarithm of 16 to base 2 is equal to 4. You can see the relationship between indices and logarithm. Since 2 raised to the power of 4 is equal to 16, then it means we can see the logarithm of 16 to base 2 is 4. In other words, what that means is that 4 is the power. Remember what we treated in our last class. 4 is the power to which the base needs to be raised for us to get the number. Remember we said that logarithm, another word for logarithm is power. Although there is a little difference between logarithm and power. All powers are not necessarily logarithms. So you need to take note of what logarithm is in this context. That's why we are specifying the relationship between indices and logarithm here. Where you have 16 written in its index form like this, 2 raised to the power of 4 equals to 16. The implication is that the logarithm of 16 to this base, in this example, is 4. That's another way of saying that 4 is the power to which the base 2 must be raised for us to achieve 16. So it is simple. I easily get that. Now, so we can say that 2 raised to the power of 4 equal to 16 is equivalent to the logarithm of 16 to base 2, which is equal to 4. See, these two expressions are equivalent to each other. Now, this form, 2 raised to the power of 4 equal to 16, is known as the index form. See, it's known as the index form of this expression. While this particular form, this one you see here, is known as the logarithmic form. Let me write this for sake of efficiency. This is the logarithmic form. And we can call this one the index form. See this, right? Now, in a similar vein, let's say similarly, if 125 is equal to 5 raised to the power of 3, then we can say that the logarithm of 125 to the base of 5 is equal to 3. Simple as that. That is to say that 3 is the power to which 5 must be raised for us to get 125. See the logic, right? So this will help us to convert from one form to another. So in general, you have to take note of this. In general, if n refers to any number, is equal to a raised to the power of x, then it implies that the logarithm of n to base a is equal to x. That is what the general deduction is. Now we can use this relationship to solve simple logarithmic equations. You understand? You have to note this. Logarithms, write this down. Logarithms to base 10, that is to say that log 10, or you can write it like this, log 10. They are called, we emphasized this in the last class before, they are called common logarithms. Underline it for emphasis. Now in common logarithms, the base number, which is 10, is sometimes omitted. You understand? So sometimes we can write instead of log 100 to base 10, we end up writing log 100. We may not write the base. Do you understand? But we already know that the logarithm, or are dealing with common logarithm, well, that's when we don't write the base, most likely. You understand? Now we can conclude that let me see to us. If 1 is equal to 0 raised to the power of 0, then we'll say logarithm of 1 to base 10 is equal to 0. If 10 is equal to 10 raised to the power of 1, then logarithm of 10 to base 10 is equal to 1. Now if 100 is equal to 10 square, then we can say logarithm of 100 to base 10 is equal to 2. Similarly, if 1000 is equal to 10 cube, then we can say that the logarithm of 1000 to base 10 is equal to 3. So it follows this particular pattern. Let me now number them. It follows this pattern. If 1 is equal to 0 plus 0, then similar, it simply means that the logarithm of 1 to base 10 is 0. That is to say that if you raise 10 to the power of 0, you will get 1. Of course, you will agree with this. If you remember the law of indices that tells us that n to the power of 0 is 1. So if 10 is equal to 10 raised to the power of 1, then this is true. Of course, if you remember that 10 raised to the power of 1 is 10, right? So logarithm of 10 to base 10 equals to be 1. You know that 10 square is 100, right? Good. So this is what we are emphasizing. If 100 square is equal to 10 square, then it means that the logarithm of this number to this particular base is this power here. Let's take example. I'll solve the one I have here in this book, my textbook. Say solve for x in the following equations. here I have the logarithm of 81 to the s to be equal to 4. And here I have the logarithm of 0.04 to base 5 to be equal to x. So let's solve this. Now you remember that let's say if the logarithm of 81, we are dealing with this one now, so the x is equal to 4. You know the equations are solve for the following. Solve for x in the following equations. So we are given that the logarithm of 81 to the s is equal to 4, right? Now, from what we have gotten, if this is true, then it implies that what? X raised to this power is going to give us 81, according to what we have discussed earlier. So this is what it simply means. So now what you do is you try to equalize the base, so that I will try to try to express 81 in terms of in such a way that the power it will be in index form, the same way the left hand side is in index form. We'll get a value in index form such that it is a number that is raised to the power of 4. That will help us to find s quickly. So let me say equalize the powers. Equalize the powers. Let me use that term. And that implies that x raised to the power of 4 is equal to, what can we raise to the power of 4 to give us 8? If you try to raise 1 to the power of 4, of course, it will still be 1. If you try to raise 2 to the power of 4, what are we going to get? 2, 4, 8, 16, it will not work. If you try to raise 3 to the power of 4, we will have the 81. 3 times 3 times 3 times 3. And it's, watch this. 3 times 3 times 3 times 3. This will give you 81, right? Now, it means you can say this is 3 raised to the power of 4. Of course, this and this can cancel that. Sorry, this and this can cancel that. Then x is equal to 3. Since x to the power of 4 is the same as 3 raised to the power of 4, it is very clear that x is equal to 3. Do you see that? So you say therefore x is equal to 3. It's as simple as that. The equation is solve for x. So since we have gotten the value of x, we have arrived at the expected answer. Simple, right? Very simple and straight to the point. Let's take this. If, that's the example 2, if the logarithm of 0.04 to the 5 is equal to x, then it means that 5 raised to the power of x is equal to 0.04, right? And you'll agree with me that 0.04 is the same thing as 4 over 100. How did I know it's 4 over 100? Refer to previous videos, you will know. Or simply put it this way. You have 2 zeros before this 4, right? That shows us that you have 4 all over 100. There's one technique I will show you here. You have 0.04. If you have 0.04, then you can do this. Watch this. This decimal point, assume this is 1. And every other digit to the right hand side should be 0. And then you have 4 over, starting from this, 100. Idea? Mark, starting from this point of decimal point, which you have assigned 1 under it. Every other thing turns to 0. So 0.04 is 4 over 100. So you can use that technique here. Or you can also take note of this. Remember that we have a number pattern like this. 0.4 is simply 4 over 10. 0.04 is 4 over 100. 0.004 is equal to 4 over 1000. You see that? So you see that the number of zeros is equivalent to the number of zeros that appear at the denominator. In this case, we have 2 zeros. So here we are having 2 zeros at the denominator. It will be 4 over 100. It's called 4 hundredths. This is 4 hundredths. This is also 4 hundredths. That is 100 th. Now, if you are to simplify this, you know this is the same thing as 1 over 25. You know, dividing both numerator and denominator by 4, you get this. And that implies that we can say 5 is the power of x is equals to 25 is the power of minus 1. How did I get that? Remember the law of indices. 1 over a is equal to a raised to the power of minus 1. Indices tells us that 1 over s is the same thing as s to the power of minus 1. Right? So, meaning 1 over 25, we can say is the same as 25 raised to the power of minus 1. And this is the same thing as, this implies that 5 raised to the power of s is equal to, let's try to express 25 in terms of the base of 5, so that we can cancel out. That will be 5 raised to the power of what? 5 square is 25. So 5 raised to the power of 2, then minus 1 here, times minus 1. Are you there? And this is this 5x. That implies that 5x, 5 raised to the power of x is equal to 5 raised to the power of. Now, these two multiplies this minus 1. Right there. These two multiplies this minus 1. Since both of them are powers. Now, 2 times minus 1 is what? Minus 2. Now, this and this can cancel out. When the base cancel out, it means that s is equal to minus 2. If you simply compare them from observation, you see the powers are equal. The bases are equal, so the powers should be equated. You understand? So by equating the powers, we get what we have here, x equals to minus 2. So it's as simple as that. You try this exercise for me. Try this exercise for me. Call it homework or assignment or exercise, depending on what you want to call it. Question 1 says, solve the following equations. So the following equations: a logarithm of 49 to x is equal to 2. B logarithm of 27 to x is equal to 3. Let me take one more. C logarithm of x to base 10 is equal to 8. Right. D, take this. X is equal to the logarithm of 0.1 to base 10 log 0.1 to base 10. This is 10. Hope it doesn't get you confused. This 10. Now we'll go to number 2. given that the logarithm of 625 to base x is equal to 4, find x. This is a of 2. Let's go to b. So given that y raised to the power of 3 is equal to the logarithm of this, so base 10, find y. We have this, given that k square is equal to the logarithm of 512 to base 2, find k. So this is what we have to be doing as our assignments for this class. Here are the answers to guide you according to what we have in the textbook here, which of course should be correct. So first of all, let's solve the following. Logarithm of 49 to base s equal to 2 as a. The answer we have here is say x is equal to 7. So after solving, I expect you to get something like this if your solving is correct, provided what is here is also correct. Then 2, question says logarithm of 27 to base x is equal to 3. What we have here is that s is equal to 3. Then let's see c, log s to base 10 is equal to 8. S to base 10 is equal to 8. The answer we have here is we say x, let me put it here, s is equal to this, let me go for d, say log 0.1 g. Our answer is this. Our answer is this, which is x equal to minus 1. Okay, let's go to number 2. Let me bring out the quick answers for number 2. Number 2, so given that log 625 base s is equal to 4, find s. What we have here, s is equal to 5. That is for number 2a. Then b, what we have is say y raised to the power of 3 is equal to this. Find y. What we have here is this. Say y is equal to 2. Right? Then c says given that k squared is equal to this, find k. What we have here is that k is equal to 3. So after solving, your answers should tally with what we have here, and that tells us that you are on the right track. This will help you to be on the right track as well. So we are through with logarithm. In summary, what we have done is that so far we have been able to do some of these things. In standard form, a number is expressed as a times 10 to the power n given the given terms, that is the defined terms. We stated all of them. If you have been following what we have been doing in this class, this logarithm class, before we proceed to the next topic, you must have learned 5 major things here. So we had 5 objectives, and I believe they have been achieved. That one of them is that you should recall and express a given number in standard form. Then secondly, you should recall the use of logarithm tables to perform calculations involving numbers greater than 1. Then the third objective is that you should use logarithm tables to perform calculations involving multiplication and division of numbers less than 1. We did that, and the goal has been achieved. The fourth one is that we should use logarithm tables to perform calculations involving power and roots of numbers less than 1. That is what we actually did in our last class. And then finally, in this current class, we solve simple equations involving logarithms. That's what we did in this class. Now, this is the last topic for logarithms. We have treated these 5 major objectives. Now, we'll be going into our second topic. Topic 2, call it topic 2. Logarithm is topic 1. Second topic is topic 2. And that is dealing with approximation and accuracy. Dealing with approximation and accuracy. So we have 5 objectives we need to cover. If you follow us carefully in this class, you get all of this done. So thank you for watching. Have a blessed day. See you to watch the next video. My name is Lucky Wanjirogan Jumbo. You can do well to subscribe to my channel, and I will appreciate very much. Thank you. God bless you. See you by next time.